It is 2 hours UTC, time for Astronomy Daily Live. This is a live stream where we gather together in a circle of friends and share a common passion for the science of astronomy and all things that are the universe, which is pretty much everything, huh? So, yeah, if there's one science that you're going to choose that sort of covers it all, it's the science of astronomy. So, yeah, as a young kid, I latched onto that and been on that rocket ever since. So, hey everybody, hope everybody's doing well today. I'm going to pop out my chat and I'm going to start up my live stream on my smartphone so I can monitor the situation, make sure that, uh, well, there's at least something going on. The, the video quality, the audio quality of of this live stream may not be, you know, the best in the world, but hey, I'm a lot into content, not just looks. If I was in it for looks, I would be out of luck. So yeah, I hope that this is providing a little bit of relaxation, a little bit of fun, a little bit of just sharing of the passion. So I think a lot of that is missing these days. Is that passion, and so yeah, I'm trying to bring that back in this format where just every single day we're just banging and banging and banging passion out for the science of astronomy in this case. Now, people are passionate for lots and lots and lots of things, and so I encourage uh, everyone to just share their passion. It's fun, it's great. I've been doing it my entire life, and not tired of it, not bored of it, not even hardly. So yeah, so hope everybody's doing well. Let's gather together in our circle and talk things astronomical. Don't don't have any real news or anything. Just sort of the regular stuff. Yeah, haven't heard anything. Haven't really seen anything too exciting. But it's the weekend, so news isn't posted as rapidly or anything else. What we can quickly do is go over to and these these live streams are not planned in any way whatsoever. So if you ever have any kind of a suggestion in terms of a topic, or if there's any kind of questions or comments um, you might have, bring them up either in chat on my Discord server, which you can see a link to down below. um, if you want to be a panelist on this live stream, you can do that. You can just send me an email, cosmiclettuce@gmail.com, and there's something in my eye, and uh, I will send you a link to the live stream when it goes live, and then theoretically you can join. So and you'll pop up as a little talking head down there, and we can expand sort of the dimensionality of this conversation, this live stream, this gathering together, and I think that'll be great. I think when that happens, I hope that that is something that uh, we all like, and I so I won't have to talk as much. I don't mind. I don't mind at all. But yeah, I think having one or two or three or 10 um, others in here chit-chatting and having the floor and all of that. I think that would add great dimensionality to this. Before I forget, and I did I did forget. I'm going to tweet the fact that I'm live now. Only 5 minutes late. At least I remembered this time. The other thing that I want to mention is that every single day it's getting lighter and lighter and lighter at the same time. At 2 hours UTC, I'm looking out my window now, right, and I'm seeing a nice orangey sunset, and so it's getting lighter and lighter and lighter. What I'm thinking that I'm going to do, probably, I mean, I'm going to monitor things, but let's actually go, okay, to a really, really awesome site. This is the MMTO site, MMTO dot, I think it's just .edu. I think maybe it's mmtoarizona.edu. Let's find out. Arizona edu. That it? Yeah. So kiddies are in the office tonight, and they are performing their task of knocking things on the floor. This is what kiddies do. That's their job, is to knock things off. Dennis R. Hands, who does the live stream on Periscope a couple times a week. He's got a funny thing. It says that you know the Earth couldn't possibly be flat, because if it was, the cats would have knocked everything off already, and that is absolutely true. If there's something that needs to be knocked off of something else, just get a cat or two, and they will perform their task extremely well. Now, I have not shared my screen yet. Shame on me. There we go. I'm going to go to infinity, and then we're going to go over to the MMT site. Interestingly enough, I don't know. Let's let these pictures roll here a little bit, because what I want to show you is something that I want to talk about tonight a little bit. Um, this is the MMT Observatory. This is the secondary mirror up there. Um, yeah, they've got actually like three. Oh, we can talk about that too a little bit. There's the picture that I wanted you to see. Now, I wonder if I can, like, just grab individual frames. Anyway, while this is scrolling through, I think what I'm going to do, I'm going to monitor. Okay, look, let me stay on task here and go to the almanac. The almanac is a PDF file that, for the MMT Observatory location, shows all the important stuff. The the sunset time, and then the different times of twilights, um, the sidereal time at midnight local time, and then the sunrise and the sunset. Um, uh, right, the sunrise, and then the moonrise and the moonset as well, and then the age of the moon, the phase of the moon uh, as well. So since I'm relatively close to the MMT, these times correspond pretty well. Okay, So today is the 13th of April. So sunset was at 1851. Okay, but look, by the time uh, by the time it's the end of April, the sun will be setting after Astronomy Daily Live starts. So let's see how late it actually gets. Right, that's going to be around June or so. So mid June, we're talking 2:30 UTC is my sunset. That's local time 19:30, 7:30 p.m. Um, so what I'm thinking I want to start doing maybe in May. Maybe in May. I mean, I'm going to monitor this and sort of play it by ear, but I would like to do some astronomy daily lives outside in nature, because really what this is all about is being able to experience nature, to experience you know the natural world, and in a very 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 real way. When we look at things, we are touching them, um, in sort of a particular way. There, what's actually going on, right, is the electromagnetic fields of those objects have extended themselves to us, and beyond us, and we are experiencing that electromagnetic field. Now we call it seeing or viewing, um, or seeing light. But what we actually are experiencing is we are in the electromagnetic field of that object. So in a very very real sense, we are being touched by those uh, objects, and I think that's really really awesome. Um, and so I think doing some live streams outside, while it's getting dark, I think that would be really really neat. So yeah, I'm definitely going to be playing that by ear over the next month or so, but we'll see. We'll see what April starts to look like. I mean, it's definitely you know dark by uh, local time 7:30, 7:45 or so. It's getting pretty dark out. So yeah, we'll see how that goes. um, I could do it on this laptop that I'm running off of now. I could also run it off of my smartphone. The disadvantage of running off the smartphone is that I don't have any way of sharing screens. So you'd sort of have to be looking at my mug the entire time, which is, I guess, not the worst thing in the world. Cheers. Got some hydrogen hydroxide tonight, HOH tonight. It's very, very calming, very, very soothing. Um, so yeah, let's go back to uh, this first this first thing. This is the MMT Observatory. Now, MMT used to stand for Multiple Mirror Telescope, and back in the day when this was first built. Hold on one second. I'm going to take care of a kitty. All right. Kitty was making just lots of noise. Couldn't think. Let's try that image. I think I did. I think I grabbed it. Putting it there. That's a good place for it. So back in the day, this telescope was actually multiple mirrors. It was 6 mirrors, uh, I think they were like 1.8 meter, 1.5 meter mirrors in a hexagonal shape. And the idea was is that you know um, well at least the plan was it's like okay we really don't know how to build any larger mirrors, right? at at the time that was the case. They couldn't build any mirrors larger than about 4 or 5 meters across. And so came up with this idea of like, okay, well, look, let's take 6 smaller mirrors and array them in a way such that uh, from one edge to the other edge you had about 6 meters or so, 6.5, something like that. um, and you'll still have the light collecting power of a 4 meter mirror, but because the baseline is a little larger than that, your actual possibility of getting some higher resolution is there. The longer the baseline, the more resolution you can actually get if you aren't limited by other things like seeing, um, which is sort of leading me into tonight's tonight's topic, which is adaptive optics. Let's talk about adaptive optics. That is something that I've been uh, not talking about here, but I was pretty involved in adaptive optics for um, a number of years until I left the university in 1998. But up until then, I was part of the high resolution um, imaging group that eventually became the Center for Adaptive Optics. So let's see, I've got to take care of another kitty. Hold on one sec. Just playing doorman. Just playing doorman. So adaptive optics is very awesome. The 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 problem that adaptive optics solves is that on the ground, from the ground, the images of targets are distorted by the atmosphere because there's water vapor and dust and air in general that's moving, that's either moving like as a wind or because of um, um, convection, right? Hot air rises. You've got all this um, stirring up of the air. Now, what's really depressing about this, right, is that you know when you're looking at a galaxy, right, that that light has been traveling through space for you know millions of years, traveling at the velocity of light, right? Traveling for millions of years, okay? And it's just going along more or less unperturbed, right? Completely just not messed up in any way. And in the last, I don't know, I want to say millisecond of its of that photon's existence, okay, of that wavefront with all that light coming in, the last millisecond or so of that light's life uh, it gets completely messed up by the atmosphere of the Earth. And on the ground, we ground observers, we call that atmospheric seeing. And uh, seeing is dependent on um, sort of two things. The first is what well what kind of seeing you actually uh, can observe is sort of dependent on two things. The first is the size of your instrument, uh, and the second is the wavelength at which you're looking at things. The um, and wavelength in sort of two senses. One uh, is the atmosphere itself. Um, like to radio. Okay, the atmosphere is completely invisible. Or more or less invisible. So we don't have really any atmospheric distortion there at all in the radio. But um, if you go down to like the ultraviolet, right? The ultraviolet doesn't really even get to the ground at all. It's completely blocked. So you can't do ultraviolet astronomy from the ground. There's just not enough signal that comes through in order to do that. Now there are some bands that make it through to a certain extent. Don't really know if those are uh, uh, detectable in any serious way or not. Don't know. Should probably look into that a little bit. Um, but in the optical and the infrared, the distortion by the atmosphere itself is uh, quite large, quite a bit, and but it gets easier in the infrared and not so easy in the optical. So so the solution to that is the so-called adaptive optics. Now, this is different than active optics. Active optics is more about um, keeping things in focus. So, focus is more or less a mechanical exercise, and defocus, can happen because of lots of things, but mainly has to do with the telescope itself, with like the structure of the telescope itself. So I'm not talking active optics, I'm talking adaptive optics. And what adaptive optics attempts to do is measure the amount of distortion that the atmosphere sort of places upon a target, and as fast as can possibly be done, uh, do something to counteract that. So we've actually measured um, the time scales of how how quickly things distort by the atmosphere, and it turns out that those time scales are on around on on the order of about 30 hertz or so, um, something like that. So uh, so you know, in order to deal with distortions on that kind of time scale, you have to be able to uh, sense the target. You actually have to collect data. Then you have to measure what the distortion is. And then you have to send a signal out to some kind of a device that does something to counteract that. And so you have to do this very, very fast, very, very fast, less than, uh, well, optimally less than 30 milliseconds, right? You have to do it really, really, really fast. If you can run at a kilohertz, that's extremely awesome. Um, so this has been done, and now adaptive optics is, I'm proud to say, is sort of a mainstay at many observatories. The MMT went through a big physical change. I don't remember how long ago now. I want to say much more than 10 years ago, maybe more like 15, almost maybe 20 or so. They took out the six 1.5 meter mirrors and put in a single 6.5 meter mirror that they had made at the Mirror Lab at the University of Arizona. And I was glad enough to be able to see that mirror being made. There's a picture of it there. Um, in in the famous spinning oven. And if you've seen, the picture behind me, let me stop sharing. And if you haven't seen that picture there, this is um, um, the first of two 8.4 meter mirrors. This was the first 8.4 meter mirror ever made, ever. And it is one of the mirrors now that is in the LBT, the Large Binocular Telescope. Straighten that out a little bit. Up on Mount Graham, which is just to the north of me. See, I'm in one of the darkest areas in the country, at at least, and I've got observatories, major observatories, all around me. I have um, at least four, right? At least four. The closest one to me now is Mount Graham, and that has the LBT, the VAT, and the um, SMT, the sub-millimeter telescope. Um, then to the west of me, I've got um, the MMT. I've got Mount Lemmon, which is Catalina Sky Survey, um, and the Mount Lemmon Sky Center, I think it's called now, and that's actually spread between two peaks. Mount Lemmon has most of the scopes. Mount Bigelow has the 61-inch and is it a 24-inch Schmidt camera? Is it 24 or 16? I don't remember now. But yeah, I spent a lot of time on Bigelow at the 61-inch. Spent a couple of years up there, not continuous years, but okay, yeah. So the MMT made its change 1998 to 2000. Cool. Yeah, I know it's been a while now, so I'm just getting old. But anyway, this was the first 8.4 meter mirror ever made, and it's still in sort of the oven. They've this bottom thing is sort of the floor of the oven. Um, they would have had walls up and then a cover on top. and they would take glass, little pieces of glass. In fact, I have a sample of that too. Should I show you that again? Okay. So here's a sample of that glass. They would get it in pieces sort of this size, sometimes a little bit bigger. This is sort of on the small side. Now, this, because I have cats, this has been dropped a few times. So there are more flaws in it than what was original, but uh, they would get this glass, sort of by the truckload. It takes, several tons of glass to make this. And so they would get this glass by the truckload, and they would examine each piece. And I don't know exactly what the criteria was, but like air bubbles are probably not good. Um, Other flaws, right? So they would reject bags, boxes and boxes and boxes of this stuff. So I was lucky enough to be at the right place at the right time, and I had free access to this stuff. And over the years, I've given every single one of them away except for this one. And sorry, I don't have any more. I don't have any more to give away. If I did, I would. I would. I love giving things away. Absolutely love it. But this is my last one, so this one's mine. But anyway, so what they do is they, inside of this oven, they would create these cells, um, these like these foam forms, okay, and they were in a specific shape. They were in a honeycomb shape, and so what they would do is they would lay all these forms out, and the forms had gaps um, in between them. So then they would place this glass on top of the forms, and close the oven up, right? Put the lid on, turn on the heater, and the glass would start to melt. Now, they make it such that it's uh, when it's completely melted, it's like water. Okay, it's that thin. It's very 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 thin. So what happens is that of course this glass melts and flows in between these frames that have been set out in a hexagonal pattern, and um, you know fills up those gaps. So it fills up sort of a bottom plate, and then these hexagonal things. Um, it's just like a beehive, right? The hexagonal shape, and then a plate on top. So they have to be able to know how much glass to put in there. So they melt the glass down. It sort of flows um, in between all these forms, all these like ceramic foam forms, and then the entire oven the entire oven starts spinning. It starts to spin, and what that does, of course, is it makes the edges of the mirror rise and the middle sink, right? So it creates a spherical shape, which is close enough. It's close enough to what they eventually want, which is a paraboloid shape that they can spin this at a certain rate, get a certain curvature to it. And then once they've got the spin rate exactly where they want it and the curvature exactly the way they want it, they have cameras inside to monitor it and all this. It's quite a spectacle. Um, uh, then they start slowly turning the temperature down. They got to keep spinning, right? Because it's still like water, right? But they start slowly turning the temperature down while it's spinning. And this can take weeks. This can take weeks because they don't want to crack it. They don't want to crack it. They don't want to mess it up in any way by letting it cool too fast or become the shape distorted and all of that. They want to keep that shape, right? So they have to keep it spinning, and they have to slowly drop the temperature down until it's cooled and solid like that. So yeah, quite an amazing thing that they can make these huge mirrors. I don't know if you can see these little things that you can't really see well. These are all little people, and I'm yeah I'm over here in the back. So yeah, I had a small part in not the manufacturing of this mirror, but actually the testing of this mirror. So once they got this done, it had to go on to the polishing tool and turn it into a parabola, and then they had to constantly check the figure of that to see how well it is. And yeah, I help with that. So fun. But one of the things that they did uh, when they changed the MMT over to a single 6.5 meter telescope is they put adaptive optics in it. And that image that I was showing, let me do it like this. Downloads, yeah. Nope, it's got to index itself. Always takes a million years to index. I'm going to take a swig of this hydrogen hydroxide while it's indexing. Cheers. Okay, there we go. Okay, let's zoom in a little bit so we can really see this thing taking its time. Here we go. So this is a secondary mirror. This is what's called an adaptive secondary mirror. And so this sits, if you can imagine, the primary mirror is the big one, is the 6.5 meter mirror. So that collects the light and focuses it onto the secondary mirror. And then the secondary mirror um, uh, reflects that light through a hole in the primary mirror to the instrumentation that's on the back of the telescope. It's essentially, like a Schmidt-Cass, right? Um, but in this case, the secondary mirror is an adaptive secondary mirror. So what you're seeing here is a very thin glass plate. I think it was maybe 2 or 3 millimeters thick, okay, and glued onto the back of this very thin glass plate are all these little motors, all these little actuators. They're like voice coils, and they're glued to the back of this thin plate. And what you can do with that is you can push them or you can pull on them. And uh, whichever way, right, you slightly distort the shape of the secondary mirror. And you can see this is quite a fine grid. A lot of work went into, figuring out what the pattern um, was going to be, what sort of the optimal pattern, what are, the stresses on this mirror, how much can you push and pull. Um, these are one of these things that you don't want to have to make more than one of, because these plates are very, very, very um, difficult to make. I believe it took them several months to make this one, because it has to be in a particular shape. And I mean, it's just like making a mirror, right? But in this case, instead of a nice thick meaty mirror that you can sort of grab onto and hold onto, this was a two, like a 2 millimeter thick, maybe three uh, thick piece of glass. So it's just absolutely insane. I think one of the first ones broke, if I remember right. There were a lot of delays, and yeah, it was a major pain. Now, of course, this picture was taken before the the front surface of this was coated, probably with aluminum. I don't think they're using silver, probably using aluminum. Um, so that's why you can see all the mounting points there. So the idea here, right, is that um, you have a sensor that can measure how much distortion is being caused by the atmosphere, and then you can very, very rapidly measure that distortion and calculate what each of these little actuators, how they have to move in order to deform this mirror such to counteract um, what the atmosphere is doing. And you have to do this very, very fast, right? You have to keep up with the atmosphere, and so that is basically what adaptive optics does. Now, adaptive optics requires one really, really important thing, and that is wherever you're looking in the sky, you need to be able to see a star, a point source star. So, most of the time, there is, well, there are stars in the field of view, but they have to be pretty bright. They have to be pretty darn bright, because you want a nice, strong signal, right? Really, really great signal to noise. So you want a really, really, really bright star. Now, the number of stars uh, decreases as you get brighter and brighter and brighter. Right? Um, there are only a couple of stars in the sky, not counting the sun, that are brighter, than 0th magnitude. Right? There's Sirius, um, Vega, by definition, is 0 magnitude. Um, what is it? Is Arcturus or Antares, are they really, really close? I know Betelgeuse is like magnitude 1-ish or so. Um, Correct me if I'm wrong. But anyway, so in order to get a really bright star in the field of view, um, that is sometimes a little more difficult. And that's one of the drawbacks of adaptive optics. Now, there are solutions to this as well, but one of the drawbacks is that you can only correct for a pretty small piece of the sky. Maybe arc minutes, maybe more like arc seconds. So very very small portions of the sky. Now, as I said, there are solutions to that to sort of widen that up, but yeah, I'm going to leave that for another time. But what if you have a target? You want to be looking at some kind of a faint QSO, quasar, um, and there's no bright star around at all. What do? Well, you create your own artificial star, and that is dun, 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 dun. When it comes around, I will grab it. Dun, 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 dun. There's a secondary mirror. There we go. So this is the MMT. Okay, the same one. 6.5 meter mirror here, secondary mirror here, but it has a laser. It has a laser, a laser that shoots up into the sky, and it is tuned to um, well, and I can't be for sure what wavelength that they're using, but they can tune it to a particular layer in the atmosphere that they can excite. Oftentimes they'll use the sodium layer, right? And so what that laser beam actually looks like when you're looking at it through a scope is it looks like a point of light. It looks like a bright point of light. And that's exactly what you need in order for the adaptive optics to work, is that you need a very, very bright point of light shining down through all this atmospheric sludge in order to sample it. And if you're able to do that, then you can do your adaptive optics, you can sharpen up the images. And that's what it's all about, is removing the atmospheric distortion. And adaptive optics does that extremely well. Now, uh, lots of amateurs, a lot of pros are turning to this technique called lucky imaging. Lucky imaging. Um, and what that relies on is a lot of data, a lot of data. The the whole idea there is that the atmosphere is very dynamic, and sometimes on relatively rare occasions, you'll get a piece of atmosphere that is very very stable, very very stable, um, and for a very very short period of time, it might be only be a few tens of milliseconds or so. Any target that you are looking at is all of a sudden going to get extremely sharp, extremely clear, because it's as if there's no atmosphere at all, right? And so you can do this technique called lucky imaging, and you know if you run a video camera for a few hours looking at, say, Jupiter, right? Well, if you're running at 30 frames a second for several hours, you've got thousands and thousands and thousands of images, and you can run through those images and measure, how sharp they are, and extract those, just extract those, and then use those, to stack, or to do whatever you're doing. And you'll get extremely awesome results, because yeah, it's as if the atmosphere isn't there at all. So that's another way to sort of deal with, the atmospheric problems. Of course, the problem with lucky imaging is that you're sort of limited target you can actually see. I mean, if you want to run 30 frames a second on, a 20th magnitude galaxy, you're going to have a problem with that. Cheers. So yeah, this, I don't know how many watts uh, this one is. The artificial star that we were using, with an instrument called Fast Track 2. Fast Track 2 um, was sort of the first non-military um, um, adaptive optic system ever made, and it was used at the original MMT, and it just corrected sort of the lowest order distortions of the atmosphere, which is focus, tip, and tilt. There are higher order functions as well, that, you know things like that deformable mirror can deal with. So, but Fast Track 2, which is the project I, I was involved in, um, only dealt with tip and tilt and focus. But we had a 5 watt um, laser that was pretty awesome. Now I think this is much higher power, and I don't know if the color's right. I don't know if they were um, uh, shooting a beam other than what would be sodium. Sodium is sort of a yellowish orange beam, and obviously this is quite green. So I'm not quite sure if this is a true color or or not. If it is, which I assume it is, they're they're just working with a different wavelength laser, which means they are looking at, well, they're having to excite other atoms in the atmosphere in order to make the artificial star. So, but still, it's a very cool shot. And as you can see, it looks like the date here is 2004. So yeah, that's going back quite a ways. Yeah, the whole idea is that they wanted the adaptive optics system to basically be installed when the new 6.5 meter mirror was installed, and I think that pretty much happened. I exited the scene before the this system was installed, but I did see um, uh, at least one of the um, prototype secondary mirrors um, in operation. So just in the lab, not really doing anything. But at that point, unfortunately, I exited the scene, and sort of fell off of that boat, which, as you can probably tell, I regret to a certain extent. That was fun. That was fun. But I was moving on to other things. So, all right. I think, speaking of moving on to other things, I think it is time for this live stream to end for today. I don't think I'm gonna let I'm gonna kind of loosen. I mean, my constraints are already pretty loose, but I was thinking for about the past week that I would be going to some shorter uh, times. Um, Number one, that's not really happening, although I'm trying. Um, but I think I'm going to stop trying that. I'm not really seeing any kind of effect in terms of viewing time. If nothing else, it's gotten a little bit less over the past week or two. So yeah, I think I'm going to go back to close to an hour or so, sometimes a little less, sometimes a little bit more. As I keep saying, I deeply respect your time and greatly appreciate you coming in. One of the really cool things about a daily live stream is that you can come in anytime you want. Okay, you don't have to come in every single day unless you want to. Um, you're welcome to, of course. But if you want to check in every week or every month or every other day, or just whenever you can, that is totally cool. Um, yeah. Tom, I know that green lasers are also used. Um, those I've seen those be used in military applications. So yeah, I'm thinking that it's possible that they change the color just for that photo, but it's also possible that they just changed wavelength and determined that that was a better one to use. So the sodium layer I think is a little sketchy, and I think I forget what the green one does, but maybe that's a more reliable atmospheric layer. So you can sort of always count on being able to make your artificial star exactly the brightness you want. Um, because yeah, and I didn't finish that. Arg. With the artificial star, see, you can point that star right next to your target. And so when you go to sample the atmosphere, you're sampling the atmosphere of your target. And the closer that you can get um, your sampling star to your target, the better you'll be able to sample that little piece of atmosphere, which means the better you'll be able to correct for all the distortion, meaning that the image will be sharper, and with sharper images means higher resolution. With higher resolution, you can see more detail. And in astronomy, that's what it's all about. That's what it's all about. Astronomy is a hands off science. Okay, everything is too far. Okay, we cannot go and touch any of these things at all, except with these things right there. So yeah, that's what the artificial star buys you, and it buys you a lot. So most adaptive optics system have it either way, right? I mean, if you know that whatever your target object is going to be near to an adequately bright natural star, then by all means use that. Use that. But if it turns out that your target is not um, next to a bright enough star, then you shoot your laser up there, you make a star, right? You make a star, and then it's over. It's over. So you can do your science, and you have much better than Hubble, infinitely better than Hubble. Hubble was a 1.8 meter mirror, and we're talking with LBT. Okay, we're talking about a 26-meter baseline. So the resolution is just through the roof, absolutely through the roof. But resolution is another topic. So I'm going to get out of here for now. I greatly appreciate your time. Thanks for all the viewing. Hit the thumbs up if you haven't yet. Share this around. Okay, I want this group of friends to grow. As much participation as we possibly can. All right, cool. I'm going to get out of here for now. Yeah, the mothership does call. So have a great evening, a great day. I will see you again in 23 hours. Exactly 23 hours from now. We'll be here again at 2 hours UTC. All right. Peace out. Cheers and all that.